morning. I am Renu Sharma, Assistant Professor, EC Department. Today I am going to start with the next lecture for Unit 2nd for the subject, that is wireless and mobile communication. The topic of today's lecture is spread spectrum modulation or SS modulation. So, in this lecture we will going to first see what is the introduction of this spread spectrum, then pseudo-noise code sequence, that is also known as PN sequence, pseudo-noise sequence, then its properties, then different types of SS modulation exist, that is direct sequence spread spectrum, then frequency hopping SS, DHSS, time hopping, and hybrid techniques, that is a combination of the other individual techniques. Then lastly we will going to discuss about MCM technique, that is multi-carrier modulation technique. So this is the last one. So I'll begin with the introduction. So basically spread spectrum technology or modulation is a wideband modulation technique. In this, it will offers the following three main advantages over the fixed frequency transmission. So basically, in case of modulation, when we are talking about wireless communication, there are different types of modulation techniques that exist. So for considering for the wireless modulation, we are using this spread spectrum transmission. So it is highly resistant to noise and interference, because when we are dealing with the wireless communication, since there is no point to point connection exists between the transmitter and receiver, so it is totally a wireless combination. Wireless network has been set up between the transmitter and receiver, so which leads to multi-path propagation with when it is installed in urban areas or suburban areas. Then there are multiple intermediate nodes exist, like trees will be there or high-rise buildings will be there, so which causes basically multipath propagation, and this leads to interference or noise. So the main advantage of this modulation, SS modulation, is it is highly resistant to noise and it is less affected with the interference. So the process of recollecting the signal spreads out noise and interference, causing them to recede into the background basically. So whatever noise will going to affect the signal, it will going to be reached back in the background. And also this SS signals are difficult to intercept, which means that it is highly coded language. I am going to discuss that how the coding will be done using this PN sequences, using this PN codes, that is pseudo-noise codes. So this is used for, highly recommended for the security point of view, for the encryption and decryption purpose. This SS technology or SS modulation is used. Then SS transmissions can share a frequency band with many types of conventional transmissions with minimal interference. These signals add minimal noise to the narrow frequency communication and vice versa. So as a result, bandwidth can be utilized more efficiently. So basically, in communication, what is the main aim of designing any system is that the bandwidth utilization should be much efficient, as we are concerned with designing the system. So these are the three advantages of the SS modulation technique. Now there are two types of SS systems are there. First one is the averaging system, second one is the avoidance system. So a DS or the direct sequence system is an averaging system, whereas the frequency hopping and time hopping and chirping systems are basically the avoidance system. So these are the three to four different types of SS modulation techniques exist, that is direct sequence, time hopping, frequency hopping and chirping, and these are classified on the basis of this averaging or the avoidance system. So this is a unique code. So this diagram, this figure 1, it is basically showing that how this PN sequence will going to change the characteristics of the input signal, or will be appended or will be added with the input signal, so that the coded language will be act as an output of that particular waveform, and then the coded language, that is the spread spectrum technology, or the signal will be transmitted over the transmission medium. So, a unique code, that unique code is also known as the PN code, that is the pseudo-noise code, is used to spread and despread the signal using the logic which is shown in this figure A. This is figure number A, this is figure number B. I am going to discuss it. This unique code is the DS, or the direct sequence known as pseudo-noise code, as shown in this figure. So, as you can see in this diagram, that this is the data, this is the original data that you want to transmit, which is this one, this is logic 0. So, whatever data you want to transmit, it is of lesser number of, it is having lesser number of bits as compared to the PN code sequence. That is the main assumption. Now, let us say this is 1 0 1 1 0. So, I am taking 5 bits as an data sequence, as a data code, or the original data that I want to convert it into spectrum technology method. Now, 1 will be shown by this logic 1 and 0 will be shown by this logic 0. Now, the XOR operation will be calculated, will be done on this PN sequence. Now, you can see the length of this PN sequence. It is of higher number, it is having higher number of bits as compared to the original data. Now, these two streams will be XORed together, and then we are getting this XOR data, that is the spreaded data, or the spread spectrum signal. Now, this is the signal which we have received, and then again it has to be XORed with this PN sequence at the receiver side, and then we are getting this recovered data. Now, you can see that I am transmitting this 1 0. This is XORed, we are getting this signal, this is been transmitted, you can say, or it is received, then again it is XORed at the receiver side, this is matched PN sequence, and then we are getting this data again. So, 1 0 we have transmitted as per this diagram, and 1 0 we have received. So, this is a very simple example. Now, you can visualize that what is the methodology that is used under this SS signal. Original data will be used, then it is XORed with the PN code sequence which is of higher number of bits. Then the XORed data again at the receiver side XORed with the same PN sequence. Now, there is main point that you have to note, that the PN sequence that is used at the transmitter side should be same used at the receiver side. Now, if it is not done, then the received signal, that what you have transmitted 1 0, now 1 0 will not be received as it is. It may be 1 1, it can be 0 0, it can be 0 1, because the PN sequence is not used what we have used at the transmitter side. So, that is the main point that you have to note. Now, this is the second diagram, this is B diagram, and this is basically showing the spectrum in terms of spectrum. Now, you can see that this is the 1 bit duration, that is denoted by TM, this is 1 chirp period, that is denoted by T chip. This is the data signal, again this is the PN sequence. So, this is basically the data, this is the PN code, and this is the XORed data. So, these two are XORed together to get this signal. So, this is the coded signal. Now, you can see in the basis of this spectrum, that is in terms of this frequency domain, this is exists between from minus BM to plus BM. Now, you can see that the bandwidth of this chirp signal, or you can say the PN sequence, is quite high as compared to BM. So, BS will be greater than BM, and this will be the coded signal. So, this is in terms of bits, and this is in terms of waveform. You can see, you can visualize that what happens in this SS modulation technique. Now, next one is, this is showing the first type of the SS modulation. Now, this is the direct sequence spread spectrum system, that is DSSS. Now, this is the transmitter part, same we are having the receiver part also. For the FHSS also we are having the transmitter and the receiver part. So, in this case, the direct sequence spread spectrum, we can see that this is the data stream, that is nothing, it is denoted by MT. Now, it is of higher, it is of lesser, it is having lesser number of bits, let us say it is 1011, then this is the PN sequence which is having the larger number of bits. These are XORed together using this modulo 2 adder. So, modulo 2 adder is nothing, it is the XOR operation. It will going to perform the XOR operation. Now, next it is applied to this balance modulator, to which it is modulated with the carrier signal which is having frequency F0, and then we are having this SS output that is denoted by ST. So, I have told you in the earlier slide also that 2 points you have to keep in mind. That first point is that the PN sequence length is larger than the mainstream length. Second point is that whatever PN sequence or the carrier signal you have used at the transmitter side, same carrier signal and PN sequence has to be used at the receiver side. If it is not, you are not, if you are not keep it in mind, then the demodulated signal will not resemble with this data stream, that is the main signal that you are want to transmit. So, this is the main criteria that you want to follow. So, that this is the direct sequence SS system, and this is the transmitter diagram. Now, this is the receiver diagram you can see in this. This is the detection of the signal, and despreading operation can be either done by active method or passive method. So, there are basically two types of method. First, so this is the receiver process of the DSS system. Now, this is showing the detection of signal, and despreading operation can be either done by active method and passive method. So, there are basically two types of method are there. First one is active, another one is the passive method. So, this is the detailed diagram, like this is the detection process, this is the antenna of the receiver side which is going to receive the signal that what you have transmitted. Then it is applied to this RF demodulation system, that is the radio frequency demodulation technique. The output of this system is nothing, it is S-T. It is applied to a matched filter or the correlator. So, at the receiver side, you can use different types of filters. So, mostly matched filters are used because of its improved efficiency, because of its improved output characteristics. So, matched filter output will be equivalent to this one, that is the narrow band filter. Then demodulation technique will be there. So, you can see that in the feedback there will be a PN code generator, and the local clock reconstruction will be there, which will going to, local clock construction will going to instruct this PN code generator that what are the number bits that of bits that you have to make as an output. So, this is the PN code generator, and this will be the output. So, M-T will nothing, it is the replica of the MT, which is the original signal that you have modulated at the receiver side. So, this is the receiver process. Now, next one is properties of the pseudo-noise codes, that is also known as PN code, that is randomly generated. It will act as a noise because it is of higher number of bits as compared to the original data bits. So, the basic properties of the pseudo-noise code is, first one is the balance property, second one is the run length property, third one is the autocorrelation property. So, these are the three properties of the PN code. Now, in general for PN code, in every period the number of plus ones differs from that of minus ones by exactly 1, that is the balance property. So, hence NC is an odd number of code. So, basically the number of ones that you have used in a code will be differ from the number of minus ones that you have used. So, that is equivalent to a balance property. Second one is the run length property, that means in every period half of the runs of same sign have length 1, 1/4 have length 2, 1/8 have length 3, and so forth. So, this is the number of positive runs that is equals to the negative run. So, which means the number of plus ones and minus 1 in a particular code will be same. So, that is the run property. Next one is the autocorrelation of periodic sequence is 2 valued, that is NC for shifts 0, NC 2, NC 3, NC and so on, and minus 1. So, this is without normalization. So, this is the autocorrelation property. So, this slide is explaining three different properties, that is the balance property, run length and the autocorrelation property. Next one is Rake receiver configuration. So what is Rake receiver configuration? This is very important topic. Now you can see there are two diagrams. First one is A and second one is B. Now you can see that there are 5 different signals which is being applied from this multipliers. This is a signal waveform. These are the attenuators, and this is the contribution from direct path. So you can see that this is the signal waveform. It is applied to this delay. So this is delay TD1, this is delay TD2, then this is delay TD3, TD4. So this is how delay will be done, and then all the signals will be added together and then it is integrated. So this is the, these are the this is the signal from the reflection, this is the signal from the direct path, and these are the delayed version. Now you can see in this diagram also that this can be also replaced by C1T, CT minus TD1, C1 T minus TD1. So C1T is nothing, it is the signal waveform, and these are the delayed version. Then this is the integrator that we have used, and this is the combiner. So this is how the Rake receiver will going to work at the receiver side, because in wireless communication, when we are talking about multipath propagation, so the signal will be received from different path. It for one will be their direct line of sight, which is denoted by this one, contribution from the direct path. Another will be the contribution from reflections, and other will be the delayed version. So all will be added together and then integrated. So this is the Rake receiver configuration. Now next is the FHSS generator, that is MTMT is the input signal. It is applied to this channel coding, then it is applied to this 1-bit coder. Local oscillator will be there, which will going to generate the carrier signal. Then this is applied to this digital frequency synthesizer modulator. This is the clock signal. Now clock signal will going to instruct the PM code generator that how many number of bits that you want to generate. So C minus 1 number of bits that is generated by this PM code generator, and then it is applied to this frequency multiplier. So this is FHSS system. Now this is the non-coherent FHSS receiver. So this is nothing, it is just showing this is the mixer side which is being applied from this frequency multiplier. Now this is the digital frequency synthesizer which will going to generate this non-coherent FHSS receiver. This is PN code generator. Now this is C minus 1 number of bits that is generated by this PM code generator. Now you can see that BFSK, that is the binary frequency shift keying modulation technique that we have used, and then it is applied to this message demodulation FSK, and then there will be early late gates will be used, and then at the output side we are using this error correction technique which will going to correct the error that has been generated during the transmission side, and then this is the replica of the empty signal which is the original signal. So this is nothing, it is the frequency hopping receiver. Now next one, third type of SS system is the time hopping system. In this case there is C which is equals to the length of PN code. This is transmitted burst in which K message bits are transmitted together. This is one frame which is having length KTM, and then this is second frame, this is third frame, this is fourth frame. So these are the number of frames, this is the time interval. Now you can see that in this diagram, that is the B diagram, the number of pulses which are spreaded together, like this one is the first pulse, this is the second pulse, these are the third pulse. So this is how this time hopping spectrum will work. Now this is the C diagram which is showing the extended version of this B diagram. So this is nothing, it is a time hopping. Previously there will be frequency hopping from one frequency to another frequency, the signal will going to hop or it will going to jump. In case of this one, there will be from one time domain, from one time to another time, then third time. So this is how this at different time slots this time hopping spectrum will work. Now this table is showing the DS method, direct sequence, frequency hopping method and time hopping method. So these three methods are being compared together. Like this one is the averaging method, this is avoidance, and this is also avoidance method, which has been mentioned in the first slide also. Now this is a single carrier system for all the times. There are different hopping carriers one at a time and single carrier system, but transmitted at different times. So basically in this case, direct sequence, a single carrier signal is required. There is no requirement of multiple carriers. But when we are talking about frequency hopping, because the original signal will going to hop from one frequency to another frequency, so to modulate it we require different carrier signals. So this is how we require different carrier signals. In case of time hopping, we require a single carrier signal, but it will be hopped at different point of time. Now this is the simplest implementation, this is the complex implementation because synthesizers are required, and this is also the simpler than frequency hopping. Now this is long acquisition system, this is short acquisition system, and this is long acquisition system. So these two are long acquisition, this is short one. There will be a near far problem, and in this case this suffered with near far problem. This will also suffer with near far problem, but it is avoided with the proper time synchronization. These are the advantages of the DS method, like it is having the best noise and anti-jam performance, it is more difficult to detect, it is best discrimination against multipath is there. Advantages is there, it is having the greatest amount of spreading, can be programmed to avoid the portion of spectrum. Its limitation are not useful for range and rate measurement, it requires error correction is there. In this case there are limitations like it requires error correction, it is critically requires synchronization, and it can be jammed easily, hence not used generally. So this is the comparison of three different methods. Now last topic of this today's lecture is the MCM technique, that is the multi-carrier modulation technique. So the use of hybrid techniques attempt to capitalize upon advantage of a particular method while avoiding the disadvantage. So after learning with three different types of individual techniques like the time hopping, frequency hopping and DSS, we can move to hybrid technique also, which will going to combine the advantage of some technique and will going to avoid the disadvantage of another technique. So basically it is a plus point of using three different types of method in a single method, that is called as a hybrid technique. So DS suffers heavily from the near far problem, which makes the technique hard to apply to systems without ability of power control, but it's implemented is inexpensive. So DS undergoes this type of problem. The PN code generator are easy to implement, and the spreading operation itself can be simply performed by the XOR port. So this is the PN code generator output. Now FH effectively suppresses the near far effect and reduces the need for power control. So however, implementation of the fast hopping frequency synthesizer is there. So basically it is used. So selection of this SFH or FFH also has its own pros and cons. Solution are there, we can use this PN with the FH, PN with TH, FH, TH or PN with both the techniques. So these are the solution of the above mentioned problem. So which means we can use this multi-carrier modulation technique. These are the references that you can consider for this particular topic. Thank you.